This video extends the ideas that we've already met around Stefan's law and Wien's displacement law, where, if you remember, we were looking at the radiation emitted from stars and relating that to the surface temperature of the star, the peak wavelength, the power output, and the radius. We're going to look at the Hertzsprung Russel diagram in this video, which is a visual representation of the luminosity of stars plotted against their temperature. And this relates to work done by two scientists independently, Hertzsprung and Russel, who were busy cataloguing the vast amounts of data that astronomers were collecting about stars at the turn of the last century. And they weren't really expecting anything significant in terms of trend. However, when they plotted luminosity against temperature, there was a real clustering of data. And that clustering of data seemed to correlate to different stages in the life cycle of a star. And so this is incredibly useful because if we observe a brand new star and measure its luminosity and its temperature, we are able to deduce and determine whereabouts in its life cycle that star is. So what does a Hertzsprung Russel diagram look like? It's a plot of luminosity against temperature. However, there are things to notice about the y and the x-axis. So firstly, the y-axis. It's non-linear. In fact, it's logarithmic. If you look at each interval, we are going up by a factor of 100. Okay, it's a multiplication as we go up in equal increments. And the reason that we would use a logarithmic scale is typically when we've got a vast range to plot. And if you consider the highest to the lowest luminosity varying between 10 to the 6 and 10 to the minus 4, okay, that's a range of 10 to the 10. That's an enormous range of data to plot on a linear scale. So a logarithmic scale effectively compresses that into a more manageable space. Now, your temperature scale is interesting to note as well, because the temperature is increasing as we move to the left, as we move to the origin. And that's the complete reverse of what we would normally do with a scale, isn't it? Okay, so please be aware of both of those features of the Hertzsprung Russel diagram and the scale that's being used. But you can see really clearly, can't you, the clustering of data. So where main sequence and the reds and the super reds and white dwarfs form, they're in quite defined regions. So if we consider the life cycle of our star, the sun, for example, I guess it's somewhere around this region here. It's kind of orangey yellow in colour, isn't it? And at some point in the future, it's going to become a red giant. So it's not going to become a super red. It doesn't have enough mass for that. But it is going to become a red giant. And then at some point further to that, it's going to become a white dwarf. So the journey that our star would take is that shown there. But another star might take a different journey. So another star might be here on the main sequence. So it's actually at a higher temperature and a slightly higher luminosity than our sun. And it might become a super red. And from that point, eventually, it also becomes a white dwarf. So you can see how a star transitions from different parts of its life cycle. Now let's have a look at how this ties together really nicely then with Wien's displacement law and Stefan's law. And let's consider the white dwarfs and the reds and the super reds. So first of all then, the white dwarfs. Well, their peak wavelength must be somewhere centrally or thereabouts in the visible spectrum, because white indicates to us that we're getting a good mix of all the different wavelengths of light. So that distribution, that black body distribution, must incorporate all of the different wavelengths of light so that when they're added together, we observe the white that the white dwarf is. That's related to its temperature. So Wien's law says that the temperature suggests that these stars should appear white. So it's consistent with Wien's law. In terms of Stefan's law, it's also consistent. It's probably worth just restating that so that we've got that in front of us. There we go. Now, what do we know about the white dwarfs? They are incredibly hot. So by the time we've raised that temperature to the power of 4, that term is really significant. So for the luminosity that we observe, that means the radius has to be quite small. Okay, and that's again consistent with them being a white dwarf. Okay, so you can see how the point in the life cycle corresponds really nicely with Wien's and Stefan's law. Similarly with the reds and the super reds. So with your red giants, they are cooler, and therefore that peak wavelength should correspond to the red colour that we observe. Okay, and it does. And Stefan's law says that these need to be quite big. So again, if we just begin by re-quoting Stefan's law. So the temperature is much lower, isn't it, than the white dwarf. So that term is much less significant. And so for the luminosity that we observe, they must have a bigger radius. Okay, so they've got a larger size than the white dwarfs. And similarly with the super reds, the temperatures are not that dissimilar. So a red giant and a super red have quite similar temperatures. But because the super reds are much more luminous, it means they have a much greater radius, i.e. they're much greater in size than the red giants. So there's very little else to say about the Hertzsprung Russel diagram, other than the fact that you need to be able to recreate this. Okay, so you need to be able to identify each of the 4 clusters and locate those approximately on a sketch. Okay, you don't need to learn the range of values for luminosity and temperature, but you do need to just remember and take note of that reverse temperature scale on the x-axis, and appreciate that it's a logarithmic scale on the y-axis. So the difference in luminosity between, for example, the supergiant and the white dwarf, okay, is really significant. Okay, it's many, many orders of magnitude different in terms of luminosity.